much everyone who joined in our session of artificial intelligence, tools and applications. So we are going to start with the presentations, whereby we'll have 4 presentations, and then after we'll break for the health break. So I would like to welcome Professor Hoyle to proceed.
Yeah, also good morning from my side. It's a pleasure for me to be here today with you, together with my colleague Nema. And today we're going to have 6 presentations in our session, which is called Artificial Intelligence Tools Applications. And the first presentation will be given by Chide Edine Tsogilemi, co-authored with Abtel Kerim Gretskui, and it's entitled Contextual Multi-View Graph Community Detection Using Graph Neural Networks. Dear Chide, can you hear me?
Yeah, I can hear you.
Okay, perfect. Then I would suggest that you give the presentation. Please make the slides visible, and maybe you can introduce yourself briefly with some words. Thank you very, very much, and the floor is you.
Thank you. Can you see the slides?
Yes.
Yes, yeah.
Ladies and gentlemen, panelists to be part of this conference. My name is Shiro Zoleni, and I'm an artificial intelligence consultant by Icta-Emos. And today I will be presenting our humble contribution to community detection in complex networks using graph neural networks. This presentation is composed as the following. First, I will start with the fundamental section, in which I will be introducing the key concepts and the problem definition. In the next section, I will be introducing our novel approach, contextual graph clustering. In the third section, presenting different experiment and evaluation metrics used as well as the dataset. At the end, I will conclude with a summary and contribution of this work and the future perspectives. Graphs, or networks, are one of the most popular data structures nowadays. Their ability in capturing diverse information and representing pattern and connection assisted in tackling complex problems. The increasing complexity of multiple domains, such as social networks, banking, and e-commerce, led to the emergence of different types of complex graphs, such as multigraphs. Multigraphs are graphs with different types of things, as presented in this figure. To benefit from the graph structure, researchers tend to adopt and generalize NM and CNN and implement these techniques directly on the graph. This led to the introduction of graph neural networks. Graph neural networks, or GNN, are a class of deep learning algorithm designed to perform directly. Attention exhibited from the left to the world of multiple variants of GNN, such as graph convolution network, and graph attention networks, and graph attention network version 2. Usually, graph neural networks are devoted to supervised tasks, whereas they can be used in unsupervised tasks using a technique called graph representational learning. Graph representational learning is transforming those graph data into a graph dimensional picture while preserving the graph properties. So, these various graph embedding techniques, we can find the graph total encoders. The graph total encoders entities, GNNs, in the graph learning. They are composed of the following parts. The encoder transforms the graph into a level representation. The decoder, which reconstructs the graph from the level representation. And the reconstruction loss function, which calculates the difference between the initial graph and the reconstruction one. One important concept about social methods is community detection. Detection is a graph clustering technique that enables the recognition of densely connected communities within a graph. The nodes in each cluster are most densely connected internally within the rest of the network. However, applying a community detection technique on graph is a complex task itself, especially when the importance of certainty information are more crucial than remaining views. The importance of these views are evaluated on the different demands. In the industry, these needs and demands are recognition, as these demands are linked to a certain business context. how communities and groups can be detected, especially using graph networks, taking into consideration the variable context of the newspaper. Attending this research lesson will divide the problem into three sub-questions. How can we integrate the graph problem? Second, how can we combine graph neural networks and community detection of complex networks? Third, how can we integrate the dynamic business context in the community detection problem? For that, we can deliver the approach contextual graph clustering, CGC. Our approach consists of three main blocks: the embedding block, fusion dynamic context block, and the clustering block. CGC was inspired by the divide and conquer method. In our case, we divide the networks based on the views, and treat every view separately through an embedding block. The embedding block will transform the view feature into a lower space representation, which will be combined later on alongside with the context of fishing in the fusion and context block. For the last step, the approach will extract the community using the clustering block. Embedding block. The main goal here is to transform the view information into a lower representation to the community. The fusion context block. Our approach applies the context directly in every group, applying the embedding with the associated context of fishing. Is a numerical representation that represents the importance of the view embedding. Its values can vary from -1 to 1. The closer the value to 1 is, the more important it becomes and vice versa. For the value 0 is measured. After calculating the contextual embedding for every view, as an engagement function, we apply the average to all the resultant embedding and transform the resultant average embedding to the next block. In the clustering block, we put the average embedding to the common algorithm. Using an empirical approach to determine the optimal number of engineering scales and evaluation metrics so it's stored. This metric evaluates the resultant communities in terms of similarity within the same community and the comparison to other communities. For the experiment, the dataset was provided for the afternoon under the Neural Business Project. This dataset consists of 128 mentions for each node. The graph consists of 5 different views with various number of ages. Each age contains 2 futures. Also, we were provided with the following business context official, which takes into consideration the view 2 as the highest priority. In the embedding block, all the group embedding must share the same image as they will be aggregated fusion and the context block. For that, we calculated the average loss and accuracy produced from all the views in a certain range of. Then we concluded that information representation, the highest accuracy score, while maintaining a low loss score, as we can see here in the figure. To better visualize the fusion and context block in our approach, we will create a graph embedding using two-dimensional representation as it's easier to present it visually. And we will focus on node. Also, we will be using the following view context partition that gives the highest probability to first to view, the view 1. After implementing the first 2 blocks, we end up with the following figure, which shows that the contextual average embedding is closer to the view embedding than the average embedding. And the product clustering block, and after calculating the beginning algorithm using a range number of dimensions, we notice that the optimal number of communities obtained using the silhouette score metric is 3, as it can produce a silhouette score equal to 0.415. After implementing our approach on the provided dataset, we were able to detect communities under the provided context, and we were able to obtain a silhouette score of 0.450. What's the outcome and our goals? In the introduction, we asked 3 main research questions. How can we anti-raise graph neural networks simply that answering using graph CGC embedding block. As we were able to use graph as a main core of the embedding block, and later on use graph to tackle the community detection problem. For the second question, how can we combine graph neural network and community detection and context? To answer this question using the divide and conquer method, as in the embedding block, we reduce the network complexity by treating every view separately. And later on, we review the context, the diffusion and context block. How can context and the community detection problem? We introduce the context of phishing that was used to indicate the importance of app based on the current context, and the conclusion next to the extracted embedding enable us to integrate the context into the view embedding directly. In this work, we introduced our novel approach. Contextual must integrate the dynamic community detection problem using graph neural networks. We also present and numerical representations that measure the importance of the information under the current context. And we were also able to successfully determine the community and context graph within various context professions. However, in any world data, data is continuously changing. Which means graph structure and relation may change. For that reason, future work these three communities. However, after explaining these results, we found that explaining the result and the community's distribution a bit difficult. We know for certain that the distribution of the communities is influenced by the population. But in what level, how can we that and how can we that the user handle? All of these questions open the door that aims to add explanation
Chihei, can you hear me?
Also, appreciation for the PR for your
Chihei,
and necessary computing resources for this paper. Wow! Thank you for your attention. Any questions?
hello, Chihei.
What's your opinion of the influence of vacuum? When you got top vacuum, not gonna lie.
Chihei, can you hear me? Chihei, excuse me, can you hear me? Chihei, can you hear me? No, she's unmuted. Chihei, can you hear me? Yes, Chihei, there is an interruption, and I'd like to ask you whether you can hear me, and if it's Chihei, can you hear me? Chihei, can you hear me? Chihei, another try. Can you hear me?
His data set will be okay.
It's fine, it's okay. It uses a very, very strong connection there. That's what he said. The screen is fine. Shihab, can you hear me?
You see? He's responding. He can hear us. He can hear.
Where can you see it? Sorry. Can you go to the chat function, please? And it doesn't work. I've already tried. So
He's saying the voice is not clear, but he can hear us.
okay, then I would suggest we proceed to the next presentation. Unfortunately, I'm pretty sure there are quite a lot of questions. Maybe Abdel Karim, we can talk later, and then you get the our feedback back to your colleague, right? Okay, thank you so much. So, however, okay, Nima?
Okay. So thank you very much. So the next presentation is on object detection model for poultry diseases diagnostics by Shabani Karim. Is Shabani here?
No, I think Shabani is online. Shabani, can you hear me? Shahani, is there a possibility that you can you see her online, colleagues? Not to this room? Good morning, Shabani, can you hear me? Yes, Shabani, can you hear me? Perfect. Thank you. Thank you very much. Good morning to you and to the colleagues in Egypt. Can you make yourself visible and put the slides on the screen? Share the screen with us. Your presentation, please. Accidents. Hello. Hello, Shabani. Shabani. Oh. Sorry? Colleagues, can you just check whether who is online with us in the room? Because obviously it looks like there's somebody hacking us. It looks like that. Oh my goodness. She'll filter later. Okay, how shall we proceed? Obviously, Shabani can't hear us anymore, and we have to find a solution for that. Is there someone from the group, from the presenters, currently available? Who is available right now? Physically, I mean. So, Nima, do you know a colleague of yours who might be available right now?
Fabiana But we cannot do anything right now because...
No, that's what I'm assuming. I mean, if you are hacked, so that might be a nightmare. Flavia, can you do that? Perfect. So then, dear colleagues, we would like to move and go forward further with the next presentation, which is dealing with investments. Maybe you can try to solve the problem there. Thank you so much. And the presentations from Flavia, the slides. Flavia, did you share your presentation with your colleagues? Okay, perfect. Flavia, if you want, you can introduce yourself using the time and, okay, for doing so. Thank you so much.
Good morning, everyone. My name is Flavia Stephen Mayo. I'm a master's student from the Nelson Mandela African Institution of Science and Technology, and I'll be presenting my paper that is titled Convolutional Neural Network Deep Learning Model for Early Detection of Streak Virus and Lethal Necrosis in Maize, a case of the Northern Islands, Tanzania.
I saw your poster yesterday. It was quite nice.
You say?
I saw your poster yesterday. By the way, are the other rooms working? They're also not working?
It's coming now.
Excuse me, can you put at least the slides from Flavia on the screen for us? Flavia, please go ahead.
So, as I introduced myself earlier, my name is Flavia Stephen Mayo. I'm a master's student from the Nelson Mandela African Institution of Science and Technology, and I'll be presenting my paper that is titled Convolutional Neural Network Deep Learning Model for Early Detection of Streak Virus and Lethal Necrosis in Maize, a case of the Northern Islands, Tanzania, and this work is under the supervision of Dr. Neema. In my presentation, I'll take you through from the introduction to the results of my work. Introduction. So, agriculture sector in Tanzania, more than 6% of the residents depend on agriculture for their survival. And here in Tanzania, agriculture contributes for about 29.1% of the gross domestic product, 67% of the total employment, a significant food source, industrial materials and foreign exchange revenues. Also, agriculture is categorized as either a source of food and cash crops production. And one of the most planted crop in Tanzania is maize, which accounts for about 45% of the country's farmland. As you can see below, there's a picture of maize. For those who do not know maize, problem statement. So growth rate is decreasing because of maize vulnerability to plant diseases. And the most devastating diseases that are affecting maize are maize lethal necrosis and maize streak virus. So farmers have difficulty detecting these diseases for early control. And for that case, this study, the research aims at filling the gap by investigating the potential of developing a convolutional neural network deep learning model for early detection of these diseases within the Northern Islands, Tanzania. Going straight to materials and method, the data set that I used, the data sets in this work were maize images, and they were collected from small-scale farmers from the 3 regions in Tanzania, that is Arusha, Kilimanjaro, and Manyara, for about 6 months, from February to July last year. And we used different mobile phones, cameras with different resolutions, and images were in JPG, the Joint Photographic Group. And we collected a total amount of 18,304 images, and whereby we distributed these images in the 3 classes. For healthy, there were about 6,072 images. For maize lethal necrosis, there were about 5,373 images, and for maize streak virus, there were about 6,859 images. That is the image of the sample images that were collected. The very first image represents a sample image of a health maize leaf image. The next image that is labeled B is the image of a maize leaf that is affected by maize lethal necrosis. And the very last image, C, that's an image of a maize leaf that's affected by a maize streak virus. So these are just samples of the images that were collected. After data collection, we went straight into data cleaning. As you all know, data cleaning is a very important procedure in every machine learning project. So in this stage, we're just making sure that the data is free from inaccurate or false data. So the things that we did in data cleaning, we removed the duplicate images, and we used a tool that is called the VCPix tool. And then we labeled the images in their respective classes, like for example, health from health 1 to the last image, the same with maize streak virus and maize lethal necrosis. And the process of renaming the images were done by a tool called bulk rename utility. And lastly, we set the images into 512, 512 pixels. So, as I said earlier, we collected a total amount of 18,304 images from all the classes. But after removing the duplicates, these are the numbers of images that remained. So, in health, yeah, just like how it's displayed there. So, from 18,304 to 17,557 images. After the data sets, we went straight into the model development, and for our case, we developed a convolutional neural network model, CNN, for the disease classification. So in model training, we didn't choose all the data set because it was we began with 1,500 data sets belonging to 3 classes, whereby we split the data sets into 500 into all the 3 classes. And the data set was split into 80% for training, the 10% for validation, and 10% for testing. Whereby, as we all know, the test percent for validation, we used it at the end of every epoch to do validation, and the remaining 10%, I used it at the end of the 5th epoch to measure the accuracy of the model and also to test the performance of that model before deploying. And then this is the model architecture. So we used a sequential model that we defined 6 convolutional layers, each followed by a max pooling layer. The first convolutional layer had 32 filters. The second layer up to the 6th layer had 64 filters each, followed by a flattened layer, then dense layer with 64 neurons. All the convolution layers used rectified linear unit as an activation function. And the output dense layer had 3 neurons, which is the number of our classes, and the softmax activation. And Yeah, just as I said, the images were rescaled to 1.0/255 and they were resized to 51251 pixels. But we also added, we expanded the training set by doing augmentation. We did random image flipping horizontally and vertically, and also random image rotation of 0.2. In model training, we used these parameters where we used 50 epochs, a batch size of 32. We chose Adam as the optimizer. And for metric, we used accuracy, and for the losses, we used sparse categorical or entropy. After training the model, these were the results that we obtained. For the training accuracy, we got an accuracy of 95.9%. For the training loss, we got we got a training loss of 12.2%. For the validation accuracy, we got 98.44%. And for the validation loss, we got 6.33%. And after model training, we now tested the model using the 10% that we had kept aside, and then these were the results that we got. We got an accuracy of 94.79% and a loss of 14.12%. And then these are the plots for the results that we got. The figure represents the plots of training and validation accuracy, and the second is for the training and validation loss. So lastly, I'd like to acknowledge Lacuna Fund and African Center for Technology Studies for funding my research. Thank you.
Asante, Flavia. Well done. I'd like to open the room for discussions. And who wants to start with a question? Flavia, the classification of the tree clusters you built was how did you do that?
The what?
The tree clusters you built. How did you do that? How did you come to the conclusion that it is the clustering method?
No, I didn't get you.
So if you go to the clusters where you put the tree elements in it to build the go back to the slide. That was one. Maybe I misunderstood, but further. Yeah, stop. So how did you do that? How did you classify that? This tree ABC.
How I put that image?
Yes.
I chose images from the different classes, then I just put
Yeah,
that.
but how did you come to the clusters?
The classes?
Yes.
Okay, so the images were collected differently and put in different folders.
Oh, okay.
Yeah.
And this is based on 50,000?
No, 500.
500.
Yes.
Okay. Yeah. Oh, okay, got it. And the accuracy of the model of 94%, is it a good one in your domain, application domain, or is it a bad one? How would you argue on the...
The accuracy is good, and with that accuracy, it says that my model is good and it can do the early detection.
Why? Can you explain why?
Because from how I know that from 70% to 100, that means you have a good accuracy. That means you can test your model well. So mine is 94, so that's a good accuracy.
So what my colleagues say from becoming commissioner that works on our application, 94%, bad. What did you think?
Okay, it works. Thank you for your presentation. Can you tell me something about the used architecture for implementing the CNN?
Yeah.
The architecture of the CNN. What did you use?
I explained it to you.
Okay, maybe I missed it.
Eh?
Maybe I just missed it, but you can maybe repeat it. Ah, okay, so an own architecture, so not anything like efficient net, it's your own.
No. It's just CNN.
Okay, thanks.
So, any further question? Can you just tell us, Flavia, about the state? So you're on the final state of your thesis? Is the thesis already submitted?
The thesis.
The thesis? Is this submitted or are you still working on it?
No, I'm still working on it. Just the research is still ongoing. I'm still not done with it. This is just the first. It's just the first objective that I accomplished. And as you can see, I have a total amount of 18,000 data set, and I've just used 1,500. So I'm still going on. It's not done, yeah.
Oh, okay. And when is it supposed to be finished, the work? When are you going to submit finally?
I'm supposed to be done by next year, June. So
By next
year, June.
Next year, June. Oh, okay.
Yes.
So you're more or less starting,
Yes.
right? In the beginning of it. Okay.
Yeah.
But well done till now. So I wish you all the best. Thank you very, very much. So, colleagues from the technique, are there any news about the availability?
Yes, everything is okay now.
Everything is okay? Oh, perfect. Thank you so much. Okay, then let's try to go back to the presentation of Shabani. Shabani, can I ask you whether you can hear us? Shabani, can you hear us? Shabani, this is Jorge Max Gomez speaking. Can you hear me? Hello, Shabani. Greetings. Can you hear me? Shabani? Perfect. Thank you very much. Greetings to Egypt and to Jamal from my side. Would you like to share your screen with us and the presentation? And I would then recommend to start immediately with it. And sorry for our technical problems here. Can you? I didn't understand you. Can you repeat? Excuse me. Shabani, can you just put maybe we can just try to start. Can you put your slides on the screen? I hope that you can hear me. Otherwise, I would suggest a Perfect. Then would you like to please, I would like to please you to put your slides and to share this on the screen and share them with us. Perfect. Shabani? Okay, then I would say that you can start. Yes, thank you. Okay, then the stage is yours, Shabani. Once again, thank you so much for being with us today, and sorry for the delay. We had a technical problem here, so you can directly start. Thank you.
Thank you so much. Let me take you to my problem setting. So I'll take a case study of my country Tanzania. So the economy of Tanzania largely depends on agriculture, and livestock farming is part of agriculture. So for us Tanzanians, for a livestock farmer, when disease occurs, we find that there's on-time support or assistance, because most of these poultry farmers are located very far where the veterinary officers are. And also, so there is the distance challenge. And also, mostly of these veterinary officers are located at the district level. And we find that one hospital can have within an image, there is only voxels, then classify in. So as you can see, there are some only voxels which are surrounding our region of interest. And lastly, the image segmentation, this classifies each pixel according to classes. So we started with data collection, and our data was collected in northern Tanzania, Arusha, Kilimanjaro, and other regions. We have a total of around 4,000 data sets, 500 for healthy, 500 for devices, 500 for cellular, and around 300 for LCD. You can see my collecting data set. So I decided to use YOLO as my documentation architecture, and the reason I chose YOLO is because it involves few computations. It is faster compared to other approaches such as RCNN and fast RCNN, and achieves few images in order to produce more precise segmentations. So as you can see, this is the architecture for YOLO object detection. The first thing we do was when we load our data set, which is images. Then after input set, therefore the platform. This platform is together are the one that are responsible for feature extraction in our images. And lastly, we have the explanation, which is we will know the number of layers, which is responsible for the visualization as well as the classification of our objects. So after we collected the images, we did pre-processing, where we started with annotating of images. We annotated them and saved them as a test files. So every image is annotated, and then we labeled our image as that from the point to see on the screen. And then we size all the images so that all of them can be of the same size. And then training forwards. So the model was trained around 100 data sets. And because you can see all the classes were balanced. 293 for healthy, 292 for LCD, which is quality, which is having 271, and somewhere 261. So as you can see, these are the training metrics. I use the MAP as well as the recall. So during the training, functioning things to 100, pushing the training improvement was observed in the last 100x, and the best results, as you can see, were obtained at around 500 echoes. So after training, I validated my data set, and this is the sample data set. The model was performing very well. And I decided to influence my model to stream, which is an open source application for the development of machine learning models. I will show you an example of how this application works. So I decided to remove this inference just for the demonstration. So here we can load our images. I'll think we're running image.
Shapani, can you hear me? Yes, I can hear you, but we can't see any kind of activity on the screen. No, we just see the slide indicating the sample demonstration and the model was inferenced on Streamline. No, yes, something happened. Shapani, it's very difficult to listen to you since it's interrupted and very difficult to understand. Can you hear me? Yes, but we can't associate it with your voice since it's very difficult to understand.